Okay, this is about quadratic functions and their graphs. So what I'm going to do is just touch on various pieces from chapter 4. I'm not going through every detail. And I just want you to get comfortable with what a graph of a quadratic looks like and kind of some basics of how to manipulate it. And I'm going to mix in pieces of what we've been doing from the other sections in chapter 4, which is solving quadratic equations, and also mix in pieces from our study of functions previously. So what is a quadratic function? Well, there's two normal or common ways of writing a quadratic function. One is shown here in standard form. It's probably the most common. Looks like f of x or y. Remember, f of x and y mean the same thing. So f of x equals ax squared plus bx plus c. We've been solving equations of the form ax squared plus bx plus c equals 0, but that's a quadratic equation, not a quadratic function. Notice there's no y, there's no f of x here. This is just simply a straight equation. Find the x's that make it true. Whereas this is actually a function. You can find all the x, y coordinate points that make this equation true and plot them to get a graph. The other normal or common form for a quadratic is called vertex form, and I'm going to come back to that one in a little bit. So we'll focus first on standard form. So what shape does the graph of a quadratic function have? Well, when you plot the points, and you can just do this by plugging in various x values and seeing what y's you get, it makes what's called a parabola. It's this shape, it's curved, it's smooth. So the shape of the graph of a quadratic function is a parabola. Either it's going to open upward like this one, or sometimes they might open downward. Probably should have reversed these here. So then let's come to here. The parabola, it'll open up if this leading coefficient right here, a, that's the coefficient of the x squared term, is positive. That will cause the graph of the quadratic to open up if a is greater than 0, or it'll open downwards if a is less than 0. And the point on the parabola, or the point where the parabola changes directions, that's this point right here where it changes from going down or decreasing to going up, that's called the vertex. It's either going to be a minimum value if it opens up like in this one, or if the parabola opens down, then the vertex would be on top, and that would be its maximum. So the point where it changes directions is called a vertex, right there. When is a function increasing and decreasing? Well, as you scan with your eyes along this x-axis going from left to right, so as x is increasing, if the function is going down, like right here, then it's decreasing. So when I would say it's increasing, let's go when it's decreasing. It's decreasing when the f of x values are decreasing as x increases, or y values decrease from left to right, or it's increasing when f of x, like this part right here, or y values increase or go up from left to right. I'm going to abbreviate capital L to capital R. So this one is decreasing right here and increasing right here. Now if you're asked where is the function increasing and decreasing, you would say, like for example, this one is decreasing for x less than 4. You just talk about the x values where it's decreasing, because 4 is where it changes, and it's increasing for x values that are greater than 4 over here. Okay, so let's practice finding some of these given a graph of a quadratic. So here's a quadratic function, and I'm going to call it f of x. On your page, you'll be able to see the graph and all the questions at once. I'm going to have to scroll back and forth, though. So for what values is this curve increasing? I mean, where is it going up? Well, it starts going up right here at that vertex, which, let's go ahead and find the vertex. Looks like the coordinates, that says 5, so each tick mark represents 1, so 1, 2, 3, and then the y coordinate is -4. So it's increasing for x values that are greater than 3, because that's where it's going up from left to right. It's increasing for x greater than 3 and decreasing over here where x values are less than 3. The function is going down. Its axis of symmetry, I didn't mention that previously. Every parabola is symmetric about a middle line. It's the line that goes right through the middle. It's always going to be a vertical line. Remember, vertical lines are not functions, so they have the equation x equals. This one, the equation is x equals 3. It's just that x value. So the equation of the line over which the parabola mirrors itself, in this example, is x equals, positive 3. I don't know why I wrote negative. Just x equals 3. Okay, x-intercepts, remember that is where the function crosses the x-axis or where y is 0. So this one has 2 x-intercepts. It's got one right there and one right there. So those are called x-intercepts. You can just read them off the graph, and this one looks like this one occurs at the coordinate point 1, 0 and at 5, 0. So you could answer this either, you could say x equals 1 and 5, or you could say the points 1, 0 and 5, 0. Either way of answering this question is fine. The y-intercept, that's where it crosses the y-axis. So looking up here, looks like it crosses right there at y equals 5, or you could say the point 0, 5. Okay, what is f of 7? Remember, when you say f of x, that means what is y when x is, for example, 7. F of 7 means what is y when x is 7. So let's go find x equals 7 on the graph here. Oops, I just almost cut it off, actually. So here's x. No, I did cut it off. Well, that was a bad problem. Let's change that to f of 4. That will make more sense. Let's change that to f of 4. So that means what is y when x is 4? Well, that I can find, because here's x equals 4 right there. If we go down to the function from there, looks like the y value is right at -3. So you can say f of 4 is -3. So for what x values did f of x equal -3? Well, one of them is obviously 4. We just found that. So x equals 4. But there's actually another value. If you look at this line, imagine the horizontal line, y equals -3, there's 2 places that hit that line. This one, the other one's right here, at x equals 2. Okay, the domain, that means all the x values that you can plug in. Now let's assume that this thing keeps going on forever and ever. I'll put some arrows here, because quadratics do, they go on forever. The domain actually of any quadratic is going to be, unless it's an applied problem where maybe negative numbers don't make sense or something, it's going to be all real numbers. You can plug in any x value into either of these equations and you'll get a single y value. So the domain in any normal problem is either all real numbers, or you can say from -infinity to infinity. The range, that's the y values that you see graphed. This is a review of function stuff that we did earlier, but remember that means what are all the y's that are covered. So as I scan this y-axis from low to high, there's no y's, no y's, no y's, no y's, and then boom, right there at y equals -4, we hit our first y value, and then for all y's up after that, the function does take on all those y values. So anything y greater than or equal to, I think it was -4, yeah, it's right there where it hit. Okay, so that's basic information about a graph. This is a lot of review of vocabulary, a little bit of new vocabulary to keep in mind. Okay, x-intercepts. There's actually 3 things that can happen on the graph of a quadratic. You could have 2 x-intercepts, such as here. There's one right there and one right there. You could get a situation where the parabola just barely touches the x-axis right at its vertex, in which case you would have 1 x-intercept, or you could have 0 x-intercepts if it either opens down and it's all below the x-axis, or if it was to open up completely above the x-axis. It wouldn't ever cross. So those are the 3 places, or 3 cases. You couldn't have more than 2 x-intercepts with a quadratic function. Okay, so this is a little bit of review, but just with a new twist. That is, we're looking at quadratics now. So let's use this data in the table to find the vertical and horizontal intercepts. So remember, vertical intercepts, that just means x-intercepts. I'm sorry, horizontal intercepts means x-intercepts. And that occurs when y equals 0. So to find the horizontal or x-intercepts, you want to look for y values that are equal to 0. And looks like right there, actually, 1, 0, and that's the only one. So the y-intercept is at x-intercept is at y 1, 0. And then, okay, vertical intercepts, that means y-intercepts. Oh, actually, I missed one. There's another one right there. Also 5, 0. Almost missed that. Y-intercepts, you're looking for where x equals 0, which is right there. So it looks at 0, 5. That's the y-intercept for that particular function. Okay, if you have an equation, maybe instead of data in a table or a graph, maybe you have an equation. Let's find the y-intercept first. They're typically easier to find. So y-intercepts occur when x is 0. So that means you want to find f of 0. You just plug in 0 for x and see what you get. Let's just compute this number. So negative 3.5 squared, let's start with that, is 12.25. I'm going to take it one step at a time here, so I'm going to write that down. 12.25. And then the rest of it I think we can do in one step. So we're going to multiply that times negative 0.75 and then add 18.75 and we get 9.5625. So a little bit between 9 and 10, about halfway. So that is the y-intercept. X-intercepts occur where y is 0. That's a little bit harder to find. So you have to set this f of x equal to 0 and then solve this equation for x. Let's make some more room here. So what kind of equation is that? Well, it is a quadratic equation, which is what we've been solving in chapter 4. Let's see, because the x part is already in a squared, it's already being squared, it's a perfect square, it makes sense in this one to solve this by using that perfect square property. So that's what I'm going to do, as opposed to expanding it all out and then trying to use the quadratic formula or something. So let's move this first term over to the other side to make it positive, to get 0.75 times x minus 3.5 squared plus equals 18.75. And then I could divide both sides by this number, this coefficient 0.75, to get the x term by itself. So 18.75 divided by 0.75 is exactly 25. That's nice. So now we can take the square root of both sides. And the square root and the square cancel on the left. We get x minus 3.5. Don't forget on the right, you've got to put a plus or minus because you're taking the square root of a variable squared. And then the square root of 25 is just 5. So now we add the 3.5 over. And let's see, if we do the positive, 3.5 plus 5, that's 8.5. Or 3.5 minus 5 would be negative 1.5 are the two x-intercepts. Or if you wanted to write them as coordinate points, remember x-intercepts occur where y is 0, so you could say 8.5, 0 and negative 1.5, 0. Just depends on how you want to answer. So with that information, you could actually sketch a pretty good graph of that particular quadratic. Okay, so here's another example, same thing, but this equation is in standard form instead of what's called vertex form. So I'll come back to that vertex form again very soon. So say you want to find the x and y intercepts of this one. Well, it's the same process. You set, to find the y-intercept, you set x equal to 0. So we're going to find g of 0, Actually, when this is in standard form, it's really straightforward because the negative 5 times 0 squared term is going to be 0. Negative 30 times 0 is 0. So you just get negative 15. And for your x-intercepts, which occur where y is 0, now this takes a little bit of work because we have to solve this quadratic equation. Generally, you can use any method you want. If it factors, that's nice. That's what I would do. If it doesn't factor, I'd probably use the quadratic formula, but you could also complete the square. Now, just looking at this one, I'm looking for a greatest common factor to simplify things first. Looks like I can take a negative 5 out of everything, and that will simplify this a lot, because then we'll have x squared plus 6x plus 5. Divide both sides by negative 5 to make that go away. So we get 0 equals. Now this factors beautifully. X plus 1, x plus 5, very straightforward. So setting the first factor equal to 0, we get x equals negative 1. And setting the second factor equal to 0, we get x equals negative 5 for our two x-intercepts. And that brings us to vertex form. So mostly we've dealt with quadratics in this form, which is called standard form. Vertex form, it was up at the top, up here. Sometimes you'll find quadratics written like that. So let's talk about that form. Okay, the general form is f of x equals a times x minus h all squared plus k. If you have a quadratic in that form, it's called vertex form, because the vertex actually occurs at h, comma, k. Right? That's where the vertex is. It's positive h, comma, positive k. This is interesting because there's a minus right there. So before I go on, actually I want to go up and find the vertex of this one right here. Okay, and let me write the standard form over here. So vertex form says f of x equals a times x minus h all squared plus k, and the vertex is at hk. So in this example, notice I'm going to match the minus sign. So I have a is negative 0.75, x is just x, we have minus and minus, so h is 3.5. We do not include the negative because it's accounted for right here. And then plus k is plus 18.75. Okay, and remember it opens up if this coefficient is positive or down if this coefficient a is negative. So this one's going to open downwards. So that's a lot of information here. You've got a y-intercept, the vertex, you know it opens down, and some x-intercepts. With all of that, you can sketch a pretty accurate graph. And if one of your dots, one of these points, doesn't line up with all the others and make it look like a quadratic, then that's a hint that you did something wrong. So we'll do that next with the next problem. Okay, so let's work on this one. It's a different function. F of x equals 1.5 times x minus 4 all squared plus 3. Well, first, does it open up or down? Well, this coefficient a is positive, so it's going to open upward. So the vertex, in this one, we have a minus, x minus h, x minus 4. So the vertex is at positive 4, comma, plus 3, and k is plus k, so comma, positive 3. So that's good right there. We know the vertex and we know it opens upward. So the axis of symmetry, that's that line that goes right through the middle. Go back to the beginning here. That's this line right here. In this case, it was x equals 3. It's always x equals whatever the x coordinate of the vertex is, because it's always going to go right through that middle. So in this example, the axis of symmetry is going to be the vertical line at x equals 4, because it's the same x coordinate as the vertex. And the y-intercept, that's pretty easy to find. Let's find the y-intercept. We set x equal to 0. So I'm going to find f of 0. It's 1.5 times negative 4 squared plus 3 is 1.5 times, oops, positive 16 plus 3. So 16 times 1.5 is 24, plus 3 is 27. So the y-intercept is at 0, 27. Next, let's find f of 2, and its symmetric point. So f of 2 is 1.5 times 2 minus 4 squared plus 3. 2 minus 4 is negative 2. Negative 2 squared is 4. 1.5 times 4 is 6, plus 3 is 9. Okay, so we also want to find its symmetric point. So that's actually easier to do once we get started graphing it. So we actually have enough information here to plot a decent graph by using 5 different points. When you plot graphs, you want to be very nice and neat. Neater than I'm being, but that's just because I'm using a digital pen. Okay, I know it opens up and the vertex is at 4, 3, so I don't really need anything beneath the x-axis. So I'm going to put my x-axis down here at the bottom. Got some pretty large y values, so let's call this 30. Let's break it into thirds. We'll call that 10 and we'll call that 20. We'll just estimate there. I know f of 2 is 9. So that's that point. F of 0 is 27, about right there. We'll go through the point 4, 3. So on my x-axis, let's go up to maybe about at least 8. 1, 2, 3, 4, because I want the vertex to be kind of in the middle. There's 8. Let's go one more. Okay, so 4, 3, just estimating is about right there. Oops, I don't know why I put that point right there. Oops, 4, 3. This point should be, I was trying to graph 2, 9. I don't know why I graphed 0, 9. Hopefully y'all caught that. So 2, 9 is right there. Now you can see they're kind of lining up in the shape of a quadratic. Okay, so we know the axis of symmetry we already said is x equals 4. So let's plot that in orange here. So that means points are symmetric over that. So if the point 2, 9 is the point on the graph, well then I can move over 2 more units, still at that same y value of 9. Or here 0, 27. 0 is 4 units. It's 4 units from the line of axis of symmetry this way. So if I go 4 more units over, then I'm at 8, 27. Is that symmetric point? And now all my pieces line up. They do look like they're in the shape of a quadratic. So there we go. There's a simple sketch of f of x. Okay, let's practice one more on this, just finding the vertex and axis of symmetry. For g of x equals negative 0.1 times x plus 3 all squared plus 5. So if the general form is g of x equals a times x minus h all squared plus k, okay, this one's a little bit harder because you've got x plus 3. So what you can do, if it helps you, is rewrite that as x minus negative 3. It means the same thing. But then it's easier to match the pieces x minus h, x minus negative 3. So h is negative 3, and then plus k is plus 5. And that would be my vertex. And then the axis, which you could call axis of symmetry, AOS, that's fine, is x equals that x coordinate, negative 3. Okay. Systems of quadratic equations. I actually did some examples of this algebraically, which is a little bit more involved. But now that we know what a graph of a quadratic looks like, you can solve them graphically as well. So it is possible for quadratic equations to cross each other either in 0 places, 1 place, like here, or in 2 places sometimes. These appear to cross only at 1 place. And that xy coordinate point that solves both equations is what solves the system of equations. So in this case, I would estimate that to be at negative 3, probably right at about negative 25 would be the solution to that system of quadratic equations. That's it for graphs of quadratics, and ask if you have any questions.